Okay, everyone, we're going to get started. I know people are excited to chat, but we only have about 50 minutes remaining. So the next event that we have today is a panel that's titled The Next Decade. And so we have a bunch of our young scientists here who are going to talk about opportunities in the SCI Institute moving forward. I'm Paul Rosen. I'm an associate professor. I've been with SCI a total of 7 years. And we're going to start with introductions of our panel, and I'll have each of them spend a few moments introducing themselves. And so maybe we'll start here with Kate.
Hi, I'm Kate Isaacs. I'm a data visualization researcher and associate professor in the College School of Computing. I work a lot on the nastiest data and sound problems I can find. And a lot of that is looking at things like networks and timelines and trying to make them understandable for really difficult problems.
Okay, hi everyone. I'm Shireen Elhabian. I'm an associate professor at Taylor School of Computing and the SCI Institute. My research focuses on harnessing advances in AI and machine learning and computer vision to actually solve problems in medical imaging and enable the quantification, the objective quantification of digital data or digital information coming from medical images such as CTs and MRIs. So in simple terms, we develop algorithms and computational methods to help doctors and biomedical researchers understand and diagnose diseases faster and more accurate with a minimal expert input. And my goal is to develop systems that are not only smart, but also efficient, practical, and accessible that can be used in clinical problems.
I'm Amir Arzani, assistant professor in mechanical engineering and SCI. So my research is broadly about computational modeling of biomechanics and specifically cardiovascular disease. And we use different tools in our research, but more focused on scientific machine learning, computational fluid dynamics as of now.
Hello, my name is Tamara Bidone. I'm part of SCI and of the Department of Biomedical Engineering as an assistant professor. Our research focuses on the application and the development of computational methods to study biological systems at multiple scales. So we run simulation of individual molecules and macromolecules up to macromolecular complexes and cell representative systems in order to understand the fundamental mechanism by which those systems actually perform and respond to different type of solicitations.
Hi, I'm Wang, and I'm an assistant professor of mathematics, also a faculty member of the SCI. My group research interests basically focus on the theoretical foundations of deep learning. Most recently, we also worked a lot on the AI for science, in particular in material science and biophysics. So we have, so it's quite broad, basically. How can we understand the different kind of cutting-edge machine learning models? For instance, in particular, we focus on diffusion models. And recently, we also started looking into the large language models.
Okay, perfect. Thank you, everyone. So I think we'd like to start today with a little bit of context for why all of you are at SCI. So can we go through again and each of you describe what originally drew you to SCI and how you think that's going to play an important role in the way that that SCI develops over the next 10 years? Oh, we're switching mics. Okay, so let me start with Bao since his mic seems to be working.
That was actually my first visit to Solid. My wife and I, we went to Yellowstone Park, and then we stayed in Solid City for 2 days. Actually, at that time, both of us liked Solid City a lot. It's quite a nice city compared to the city I was before. And then we you know, a lot of uncertainties. So then we thought in the future, maybe come to Solid City and work here is a good choice. And then in around a year, then I was applying for a tenure track position. Then I saw University of Utah has an opening. Then I applied. and also certainly apply to different places. Finally, well, good thing is I got an offer from here, and actually, after I finished the interview, then the whole campus was shut down, and because of COVID, that was 2020. Well, I have already got the offer. Then it was a difficult decision at that time, but I feel it's a good fit for me. Like when I visit here, it was a 2-day campus visit. I talked to different people at the ski. They are actually it's more like interdisciplinary, but a lot of people are actually very mathematical. I talked to different folks, and also I talked to the faculty member in mathematics department. They are somehow like more mathematical, but here ski also also quite mathematical, and then this makes me feel it's actually quite a good fit for my background. Then discuss with my wife, and then finally both of us decide to move here. And I have been here for around 4 years. So far, everything was quite nice. I have make my life actually quite busy with several very talented students. One thing I feel still not finished yet is exception more collaboration with the ski members. Yeah.
Great. Tamara, what drew you here, and how do you think that impacts the future?
What's the question again? Sorry.
What drew you here to ski, and how do you think that impacts the future?
So what made me come here initially were basically 3 main factors. So the first one is the obvious one, which is the interdisciplinarity of this place. So coming here and having the opportunity to work within a university and with different departments, starting from in my field, biochemistry, Huntsman Cancer Institute, physics, and the School of Computing, obviously. So there was a source of attraction for me. And then the other 2 reasons that I want to mention is, first of all, the emphasis on scientific computing. So for the type of simulations that my lab is doing, which are based on all atom modeling and large-scale systems, so the expertise in advanced scientific computing was very attractive again, and something that I valued for our own research. And then the third factor is itself the way that ski is organized in terms of what it offers. We have a big team of developers, we have staff members, we have editors, we have a lot of resources within ski itself that makes our life within the university still very academic in terms of mission and objectives, but also a little bit, facilitated in this sense, thanks for what ski offers to all of the components of ski. And part of your questions was where we see.
How does that influence what you see over the next 10 years in ski?
What does it influence? Well, I haven't finished leveraging those 3 factors. So I keep leveraging more collaborations. I keep leveraging more software development within the team in ski, high performance computing, and parallelization for the code that we use. We are interested in a number of biological systems. So we start from adhesion proteins. Now we are moving to cytoskeletal proteins and cell models. So all of these present different aspects that all interface with software development as well as high performance computing. So I think I haven't finished to leverage what ski offers up to today.
Great. How about you, Amir?
So I think what was already said, the interdisciplinary nature, and I want to add that, all of us here at SCI, we're under the umbrella of computing, and we all love computational sciences, which is amazing. But what's even more amazing than that is that, each of us comes from different backgrounds. Some of us have more engineering backgrounds, some are more on the computer science, applied mathematics, biomedical sciences. And again, what's even more amazing than that is that many of us touch multiple of these areas or are experts in multiple of these, different disciplines. And that's really what's attractive about ski, and I think that's going to be a very strong factor that's going to drive, the growth of ski and being a leader and in the computational sciences and making impactful research.
Shireen?
So my story is a little bit different. What drew me to ski is my husband. So I spent the first 5 years in my marriage long distance relationship. I spent my marriage while I was doing a PhD at the University of Louisville, and my husband was a postdoc in Vanderbilt and then in Illinois. And he got a postdoc position here at the university. And I said, okay, let's, I graduated from my PhD in December 2012. And then I don't have plans other than going to academia. I want to be a researcher. I want to be a faculty member, but I don't have a specific place. So I use my husband to guide this. Like, okay, you're going to Utah. So, and I like I visited here in December 2012. I like the mountains. I like the atmosphere, the community. So I started reaching out to different departments. And the first choice was ski because I like from visiting their website, from seeing the faculty there. I like the mission of leveraging computing to make real difference. And under one roof, you have multiple disciplines, top leaders in different disciplines working together, passionate to make a real difference in different applications and to make our life easier. So I said, okay, let's reach out to faculties there. And this is where Ross Whitaker and Guido Gehrig offered me a postdoc position. And since then, I have been mentored by senior faculty at the Ski Institute who have essentially shaped my career now that you're seeing me, the educator and the researcher that I'm now. I also, like what kept me at Ski is the spirit of collaboration and the spirit of working on high impact problems and having direct access to application domain experts and collaborating with leaders beyond Ski, like on campus, beyond the University of Utah, having Ski as the collaborative hub that facilitated all these connections and having this mentorship that actually guided me, okay, what should I do next and what are the big problems that I should be hitting next. I think this is what kept me at Ski for more than a decade now, and I'm proud to call it as my professional home. Now, for the future, I'm working in AI and medical imaging, so I really want to contribute to establishing the full potential of AI in medicine and biomedical applications, and to really translate our research out of papers, out of our desktop applications to where it's actually being deployed, and to make this in a safe way, in a reliable way, in a way that doesn't really replace medical professionals, in a way that augment their expertise, make their workflows and more streamlined, more efficient, to maximize resource allocation, and to make a difference in human health. I will stop here.
Thank you, Kate.
Yeah, so very similar to many people, what drew me here was both the people and the problems. I think that Ski has also had a lot of influence on me since before I came here. So even like as an early graduate student, Valerio, Chris, Sean and Alex, Josh had so much positive, oh, we met really early too, but so much positive impact in the community that I'm in, the many communities that I'm in. And then, you know, since coming here, just more and more people. And I really like this interdisciplinary style where we can reach a lot of people who are working on important problems. And as long as our research remains driven by those problems, I think that we're always going to do important work. And I like being at a place that encourages that and celebrates that so actively. And I think with where we're going with that, well, in the last 30 years, the way in which everybody is using computing across campus and further on has changed and grown. And so I think that means that the ways in which the Ski Institute needs to support these different kinds of computing researchers changes. And so we have to think about, well, we want to keep our core research aspects of what are the problems that we can only do with the kind of research that our expertise has, and let's continue to build in those directions. But also, what are new ways in which we can better serve the community in which we're embedded in? because I think another important thing about us is not just who we are, but the greater community that we are a part of here at the University of Utah and beyond.
Great, thank you very much. Appreciate all those answers. Okay, so now I have a question that's obviously been very relevant in recent news. AI happened, but it turns out that AI is not actually a new thing. We've been doing various forms of AI for many years here at SCI and in computer science in general. And so my question for the panel is, can you discuss the new role that AI is now going to play in science and maybe what isn't so new about AI these days? And maybe we can start with Shireen.
Okay, yeah, because I'm the older.
You mentioned AI when you were talking about the last question.
Okay, so I guess over the past couple of decades, we have witnessed the transformation, a real transformation of how AI being used and leveraged in different applications, including medical imaging and healthcare. And couple of decades ago, AI was just, even one decade ago, AI was just a new tool, experimental tool that is showing promise, but it was limited by the technology back then. And it was operating under, it was useful in a way that it automates what's obvious to the human expert. So for medical imaging, for example, it can detect obvious issues, obvious pathologies in images, but it cannot go beyond what a human can detect, simply because it was operating under the constraint of data scarcity and the limitation of the computing power. Nowadays, the picture is quite different. The significant leap of computing resources, the availability of data in different domains, even algorithms and tools that will help AI systems transfer knowledge from domains that have a lot of data to other domains that still, till now, it has scarcity of data and it cannot be directly, like AI cannot be directly applied to it. All the combination of compute, knowledge transfer, and availability of data in different domains have reshaped what AI can benefit or can impact different domains, including healthcare and other high stakes applications. So now AI has a different flavor. It is actually going beyond what the human can detect from the data. It's not only about automating the obvious, it's about deciphering what is there in the data that's hidden that we as human beings cannot actually detect. But there's a big however here. It's how we view and consider AI as a powerful tool and how we use it in problems that are of high stake. It's not about AI making decisions independent of human experts. So I'm talking about, for example, healthcare. It's not about replacing medical professionals. It's about augmenting their expertise, streamlining their workflows, but in a way that is still have the human experience and judgment and empathy and all this experience over the years of seeing patients come in the table to audit what is the AI is giving us.
Thank you. Amir, do you have anything to add to that?
Yeah, so we do quite a bit of work on scientific machine learning, and the way that I see machine learning and AI is a new toolbox added on what we already have. So we have all these, more traditional computational toolboxes that we've been using. Now we have this additional, very exciting new toolbox. And so we can either figure out how we can find new applications that make sense for this new toolbox, or for some of us, we can figure out how to contribute to fundamental advances in AI, either tailored towards a specific class of problems or more broadly even. So that's, I think, where the interesting part is. And we have to realize that there are only certain types of problems that could be solved with AI. There are certain problems that AI is not so great. And I think what's perhaps more exciting for the scientific computing perspective is that there are problems where you can synergistically combine AI with the more traditional type of modeling that you've been doing more historically. And that's, I think, where perhaps AI becomes really exciting to many of us that are more trained on the traditional computing part. And that's one area that my group is working on.
Great, thank you. Bao, do you want to add anything to that?
Me? Okay,
Yeah.
sure. Yeah, I think AI indeed plays a fundamental role in scientific computing. In particular, I think two aspects. The first one is in scientific computing, there are a lot of things you cannot just write a analytic function to explicitly describe that. For instance, like those complicated many-body interaction, right? In classical, for instance, like density functional theory or even molecular dynamic simulation. I remember they did something called force fields, right? Actually, this force fields, they did some experiments and then they try to fit the experimental results using some like simple multilinear regression. And then, well, why not use a more powerful model like this neural network? And in density function theory, for instance, you have this exchange correlation function, right? Then a better way, I think, because we don't know the exact expression, right? So then we simply put a neural network, try to make it somehow data-driven. So that's one area. Basically, a lot of nonlinear function we don't know. We don't have explicit form, so then we use a neural network to approximate it. Similar as reinforcement learning, we don't know like those policy function or value function. We use a neural network to approximate that. Then another, I think, fascinating area is about those generative models. For instance, you want to solve some inverse problem, right? The solution space is exponentially complicated. So then how can you solve this problem? You cannot just like go through all these possible cases. A better way is through sampling, right? I try to generate some samples from the solution space and with some guidance. Maybe the solution is not optimal, but at least somehow better than this random guess or like trial and error. Right? So that's basically, I think AI plays an important role in this solving large-scale inverse problems. Yeah.
Perfect, thank you. So I want to take a step back from AI a little bit because I think a lot of people would agree that it's pretty much at the top of the type curve. There's still a lot of space for traditional computing. So I would love to hear from the panel some thoughts on the role that more traditional methods that we use in scientific computing and how they will play a role over the next decade and how they're still important. And maybe we can start with Tamara on that one.
Yeah. I will relate to AI with the purpose of sharing how I think that traditional computing and simulation methods can help do what AI cannot. So in my experience, I've seen a lot of reconstructions of protein three-dimensional structures. One of the most popular software in the field is called AlphaFold, where we introduce a sequence of amino acids and we can get a three-dimensional organization of those amino acids into a three-dimensional protein structure. So the advantage that we have there from the application of machine learning and AI is that those regions of the proteins that have high sequence similarity with something already in the protein data bank are reconstructed very accurately and others are not. So we have an idea of where to focus and where to develop new methods that are not compatible with the prediction from those tools. Another example I have, again, in the field of protein modeling is when we try to reconstruct a protein conformation starting from different stages of protein dynamics. Those structures are unknown, and with the help of machine learning, we can have a prediction that can inform crystallographers and experimentalists. So in other words, where AI cannot give us a final answer, it will give us an informed guess, or it will tell us, I don't have an answer. So we can better apply what we know and other approaches to answer those other questions. So I believe that the focus that we can have now with the application of those new tools is benefiting from the tool itself, so that we can apply our theoretical modeling, our large-scale simulation approaches, and our Newton equation of motion to understand the dynamics of those complex systems.
Thank you. Kate, would you like to add something to that?
Yeah, so I think one thing is that AI continues to run on traditional computing. And because, as people pointed out this morning, traditional computing has moved to allow AI to run at the scale that it needs to, I think that will continue. I mean, I think things are going to be partnerships between traditional methods and AI methods. And throughout all of this, the thread is going to be that, you know, this is all done for us, right? And that means that people are going to want to understand where this comes from. But the point of science is, in many sciences, is to make fundamental understanding. And I think it's going to be really important on both the traditional and the newer methods in computing to figure out what it is we need to make more transparent to all of the people at the other end, both of like, where did this data come from? What methods are used, whether they be traditional or AI?
Amir, do you have anything you'd like to add?
Yeah, I think I quickly add two things broadly. First is that in a lot of disciplines like engineering, generating large data sets is not easy. It's really, really expensive and difficult. So that's one area where traditional computing comes into play. We've been using traditional computing as a way to generate data to then build these machine learning models and test them and do more fundamental machine learning work. So traditional computing is serving as a data generation. So that's the first aspect, so that makes it still relevant. So the second aspect, as Tamara also mentioned, is we engineers, we often like to solve new problems. We want to find problems that there's barely any data for it, right? And understand fundamental mechanisms. So we can't really do that with like data-driven approaches. We have to build fundamental scientific models, and then if they're sophisticated, we numerically solve them using traditional scientific computing. So I think traditional scientific computing is still going to be very much relevant.
Perfect, thank you. Shireen, I see you agreeing a lot. Do you have something to add?
Yeah, maybe a couple of points. So
Sure.
traditional approaches are still highly relevant. I think there are scenarios where AI is basically impractical. I agree with Amir that a lot of applications that are not yet data heavy, and there is a significant domain difference between MOCU data or ImageNet data and the application specific data. This is where there's a big question mark how we can actually build AI models that can be reliable and generalizable in these scenarios. And this is where we fall back to traditional methods and computational methods. Another thing is that traditional methods still offers a greater transparency of what they are actually doing. They are not a black box. Although there is now like a huge topic in AI where how we can make it open box or white box and how we make it transparent and understand why it is making these decisions, but it's still traditional methods are offering by design, by construction, a transparent solution of why a decision is actually has been made. And in applications like healthcare or legal applications, why a decision is made is more important than what is the decision itself. Another point is in industries like regulation industries where everything has to be approved in order to be deployed, like healthcare and aviation. Traditional methods are still the mainstream because they are well understood. Their behavior is well understood. They are well established compared to black box AI systems.
Great, thank you all. Okay, so I want to switch gears back a little bit. So when each of you were introducing yourselves and why you came to SCI, I believe every one of you mentioned collaboration. So obviously that's a pretty important part of what SCI does. So I would like to get some of your thoughts on sort of the collaborative history that you've seen of SCI and what you think the collaborative future of SCI, much emphasis on the collaborative future of SCI, of course. And maybe we can start with you, Kate.
Yeah, so I was first introduced to SCI through a collaboration with a national lab. It was Lawrence Livermore, which is a mission of science in the national interest. And this was in the context of a lot of high performance computing simulations. So everything like Department of Energy lab, a lot of energy simulations, but also medicine, fundamental science, astronomy. So it was very, I've always really loved this combination of science. And the other part of science that I really love computing because it gave me the ability to do what I really love doing for a problem much bigger than I had. And I think, as I mentioned early, looking forward, we can now expand beyond that. So one thing I think that both of us have been doing recently has been with the initiative bringing in more of the digital humanities. And so I think we can expand I think we should always keep to our core ideas of scientific computing, but expand that horizon. And because other areas of study are getting, I guess, more of what we consider scientific. And then like another thing I've been noticing, of course, is how do we, as everybody becomes more capable of doing computing, how do we sort of bridge gaps to get to the kind of computing they want to do? I'd like to point out Jess State over there with running the SCI co-op of cyber infrastructure professionals to help what we do reach even more people.
Great, thank you. Bao, could you maybe answer that question as well?
Sure. Yeah, in terms of collaboration within SCI, I think there are a lot of opportunities. Actually, this has happened a lot. For instance, for myself, every time I want to develop a highly scalable, like a very system that couple my the theory and algorithm we have developed, but I myself is not an expert on systems. Then I can talk to the people here, and hopefully that will further enhance my own research. And also in terms of high performance computing, right? So that's also something I myself, my background is actually mathematician, right? And then I can leverage the skill to enhance this HPC, also for the application side, in particular like biomedical imaging. That's we have been working on that. However, I myself certainly not an expert on that. That's through talking to my colleagues. I can certainly know what's the core problems there, and then how can I leverage my own expertise to solve this. So this actually was remarkably important for my future research. And yeah, actually, then this collaborative environment here is quite helpful. I remember like last year, we were talking about this diffusion models, and then we immediately talked to several folks here, and then certainly immediately we had a better understanding of this, and we know what our colleagues, what they are doing and what we are doing. Then we basically merge these ideas together and see what maybe some remarkable opportunity will happen.
Great, thank you. Tamara.
Yeah. So in terms of collaboration, the way I was thinking about it when I came to SCI was really having the opportunity to nurture those in-person collaborations and speak with experimentalists and physicists to do the modeling and the computing that my lab is doing. Right now, I think a success in the collaboration can occur when actually the person in another domain, which is no computing and no simulation, can access your software, work with it, and carry on its or her own experiments, even without this interpersonal exchange. So the way I see collaborations moving forward is really to leverage those interpersonal collaborations and in-person, exchange of ideas and knowledge to develop models, but then creating the interface, making the code open source, and actually having the future a collaborative environment that occurs in the absence of in-person, necessarily in-person exchanges.
Shireen, would you like to add something?
Yeah, maybe on the future side of things. So as various academic fields are increasingly need to work together to address big problems, impactful problems to in different applications, I think SCI, with the already established foundations on collaborative work, the community, the sense of family within SCI, I think it is well positioned to lead these types of efforts, because it is a hotspot. This is how I call it. It is a hotspot of collaboration. Now, in order to enable this, I see how, in my view, I see the way that we can leverage this is to basically start deepening our partnership with other departments in main campus, in upper campus, even beyond the University of Utah nationally, and spearhead projects that are at the interface of multiple disciplines, computational, AI, application specific, and use that to basically grow the network of what can SCI do. And I think SCI, not only for University of Utah, SCI is well positioned to set a standard for a lot of universities nationwide, to how a university can leverage the collective expertise of their faculties and their departments so that they can make a difference.
Perfect. Amir, do you have anything to add?
Yeah, I mean, just as Shireen said, I think what's really amazing about collaboration at SCI is that every one of us represent a department. We have multiple departments that are represented by SCI faculty, and as SCI is growing, that representation is just going to increase. So, I mean, each of us have very close ties with our home department, and we know people and what the research is going on. So the role that we can play is that you identify interesting, exciting problems, domain problems that require computing, and then build interdisciplinary teams to tackle those problems. And I think what's really exciting is that a lot of times these problems, you advance those domain the domain problems, but at the same time, you need to advance computing too, to be able to tackle those problems. So it's a two-way benefit between advancing computing and advancing your home department or the specific domain problem that you're working on. And that's, I think, one of the big impacts that SCI can play at the university level.
Okay, perfect. Thank you all. Okay, so a lot of our keynote speakers had a bit of sage wisdom for the crowd, for people who are up and coming, but you also have several years of experience. So I'm wondering if each of you has a little bit of advice that you could share to graduate students or maybe some scientists who are a little bit earlier in their careers. And I'm going to put Kate on the spot to start with.
So, I mean, I think, I hope it's come through that, like, I really value all of the people around me at SCI, and I feel like I've learned so much from so many of them, and it's in like bits and pieces, because I think it's very easy to be intimidated around here of like, wow, these are amazing answers, and I love the work that's going on. And I think especially early in your career, it's extra intimidating because you don't have as much of who you are to go off of that. And yeah, look at what they do and what you admire and think, what can you incorporate? But also realize maybe what you can't, or rather really don't want to, because also your unique perspective is really important to what comes down there. So I think like a lot of graduate school was figuring out like, wait, but what is it that I really like to do? And then where does that fit in the bigger picture? And yes, how can I speak better like somebody, or write better, or manage better? But also how can I be myself and realize that like that is its own contribution, even if I don't see what somebody else doing it like that. That's maybe because that's a piece that's missing somewhere. So do enjoy both those things.
Shireen?
Yeah, so 3 things. First is basically stay curious. Like learning never ends, really. Whatever the stage you are, like every day I'm learning from my students, from my staff. Every day I'm learning their viewpoint. It's basically enriching how we move forward. Like so stay curious. Don't stop asking why things work and why things fails, because this is where insights come in play. This is where ideas starts to come, because seeing things failing is actually is a trigger of how we can make it work. The other thing is, again, back to the spirit of SCI collaboration. Mostly impactful solutions. If you see it like out there, any solution that is addressing a significant problem that has been impactful, it's not a one-man show. It's basically coming out from a team that is diverse, that have has different perspectives, different backgrounds, different even applications, and even different languages in terms of like the application domain language. So embrace collaboration, learn how to communicate effectively your ideas to not only technical audience or not only peers and faculties in your own department or in your own research area, but also learn how to communicate effectively outside your domain, outside your research area, and learn also how to listen actively. And this is basically this two-way street will help you go and do amazing stuff. The third point is be resilient. So this has to be there. Like if the research path, the path to research and innovation is not a free lunch. It's not easy. You're seeing a lot of people, they are seen to be pioneers and top leaders, but their path is not easy. Like all these stories that you're hearing from like everyone, the path through this is a lot, there are a lot of obstacles, there are a lot of challenges and setbacks. And the only thing that make anyone thrive this and go to the next step and do the breakthrough is the resilience. Learn from your failures. We are learning, everyone is learning, like to move forward, everyone really needs to learn from the failure and there's a story that we have time.
Yes, we got plenty of time.
There's a story that I always use with my students, especially when papers get rejected. Fourier has his paper on Fourier's series rejected for 8 years. And his advisor Laplace, he thought he was crazy to decompose a signal into a bunch of sines and cosines is a crazy idea. And his paper was rejected for 8 years. And now Fourier transform, Fourier series, this is the basis of signal processing and image processing. And this is the whole, the conceptually is very similar to AI and deep learning, deep networks, learning bases or learning features from images. But it all started, I don't know, centuries ago with a paper that was rejected for 8 years. So please, if your first paper got rejected, don't say I'm quitting. Don't say, oh, okay, I'm not doing this job, because the resilience is what will make you 10 years from now, a researcher or a scientist or an engineer who had a lot of ideas and innovations, and you're making impact. Thank you.
Thank you. Fantastic. Amir, do you want to add something?
Yeah,
I know it's hard to follow up.
Yeah, because Shireen covered everything. I'm going to just say what I always tell my own students. The best investment you can have is yourself. And the best way to do that while you're a student is by learning. You have a safe environment that encourages learning. You get rewarded for learning, right? This is a very safe environment to do that as a PhD student. So just emphasize learning and different forms, reading, different things, and make sure you do that every single day during the course of your PhD. And don't forget to focus on the fundamentals too. Don't forget about fundamentals. The people that make the best, as an example, advances in AI are those who have strong applied mathematics backgrounds, in things like linear algebra or optimization and statistics. So just don't forget about the fundamentals and focus on learning and investing on yourself.
Great. Tamara?
Yeah, he stole my answer. I was about to say that this is an advice that I have never given, but I'm thinking recently that I will give it, which is solve with pen and papers your computational problems first. And I would say that, all of the code that we use and the software that we use as users is very exciting, and sometimes we get so excited that we forget what's behind the scenes. So we should really pay attention to that. Get excited, but not to that extent. Go back to the equations that are implemented. I would say practice them yourself in your own coding language. And we saw an example from a previous keynote speaker of, his own code developed, which is still valid, but just rephrased nowadays. I think that is really important for making progress in the use of the software or the modeling framework that you are currently doing.
Bao, do you have anything else to add?
Yeah. So I want to mention one sentence from one of my friends when he was in graduate school. He worked with Stephen Smith, a very famous mathematician. Then his advisor essentially told him just critical thinking. So just when he started his PhD, I think this word is very crucial, in particular if you are doing research. Then at the beginning, we need to think about which problem to work on, right? Whether this problem will have any impact, rather than simply like pull out some existing code from GitHub and then try to apply this code to your data and then write a paper. If the results are good, then that's it. If the results are not good, add a skip connection, changing the convolution filters. Don't just do something like this, right? Just think about is there anything fundamental, right? So we need to, this like critical thinking. Maybe I think from the mathematical viewpoint, we need to have something like fundamental research rather than just a simple application. So that's, I think, one of the most important things in my mind. And next is, I think somehow certainly need to talk to people in different areas, try to identify what's the real important problem, right? As, for instance, if you stay in mathematics forever, then maybe what you are working on is either those long-standing problem for hundreds of years, and I believe you cannot solve that. Because it's already there for hundreds of years. And then if you are working on some other, like maybe some incremental problem, you solve that, but there is no impact at all, right? So in some sense, you do need to talk to people in different areas.
Okay, thank you. So we have a few minutes left. Are there any audience questions for our panel about the next decade? Please, Guido.
Very nice discussion. Thank you. So I have a question about collaborative. So as many of you know, I was a ski faculty for 8 years, highly collaborative. Shireen knows that too. My students now are worried about being too much collaborative because of job search. So I don't know if any of you have seen, even my university, I don't tell you what it is, it's New York and then Swiss University. I'm ranked by a DA index. It's discipline only index. So of course my D index went down from the H index by half. So I'm no more tenure track, so I'm not worried about that. Nobody has to rank me. But I don't know if you have seen that or heard that with your students, that too much collaborative, they don't want to submit to some medical imaging conference. They say, if I want to be at Meta or Microsoft or Google, they would say it's not enough computer science. So I just spread that out. I don't know if some of you have seen that or heard that. So it's terrible for collaborative research if your students think about that.
Maybe I can answer this question. Yeah, this is certainly a trend. Even in mathematics, people want to submit a paper to those high-profile venues, right? So because those conference, those are what the people care about. So for me, I usually talk to my students like, certainly you need to do your best to try to have papers in those venues. Meanwhile, those interdisciplinary venues certainly also very, very helpful in particular in the future. If you want to stay in academia, you don't want to work a problem forever, right? So you do need to explore collaboration in different areas. Just maybe do your best to get things in different areas.
You want to go ahead, Kate.
Yeah, I mean, I think there's, this is why it's always this balance between the like fundamental research we do and the fact that it's problem driven, and that hopefully both strains of publications will be happening. It's unfortunate there are institutions that don't see that the publications outside of your area, that's like the impact, right? That other people might not be having. And I think so some of that is probably there needs to be some careful thought about, okay, which problems make sense to collaborate as researchers, and what problems make sense to collaborate through other means that perhaps institutes like these can provide.
Yeah. Okay,
Do you
thank
have
you.
1 minute?
I mean,
Yeah, it's a hard
That's
Yeah.
something.
So in my research group, I work under a little bit different paradigm. We use applications as a motivation to tell us what are the technical challenges that this application is bringing to the table. And then we sit back and say, okay, is this challenge is so specific to that application, or there are class of problems outside this application that if we develop a solution, if we develop a method, it can benefit. And this is the idea of, okay, we do foundation methods that are actually motivated and driven by application, but the method itself can, either with tailoring or even out of the box, can be applied to at least more than just this application. So I think if a student starts to think, okay, my paper does address a specific application, but discuss how this can be generalized to other classes of problems, I think this will be a good balance and a good dissertation at the end of the day, because you're not really tied to a specific application. You are more on the foundational side of things, where you can innovate computational methods and AI methods that can be applied to several applications.
thank you.
Okay, great. We're out of time, so let's thank our panel. So I believe it's lunchtime. Do we have any special instructions? Okay. Out and around. It's right inside of there, but we don't know if we can go through that way. Okay, thank you. We'll be back at 1 o'clock.